So my name is Rocha. I'm from Brazil, and I do a postdoc in Leiden for about 4 years now. This is my third postdoc. I've been traveling around a little bit in Scotland, after Brazil, Denmark, and now I'm here. And basically in Leiden, I work with the James Webb Space Telescope, and I try to use data from the James Webb Space Telescope to find signatures of complex organic molecules. I know that there are some biologists here, so perhaps you're going to say that these complex molecules are not too complex, but then let's think about it, okay? Okay, so let's see. Let's go to travel all the way back to the beginning of the solar system, to the beginning of the star formation, and see which kind of material we have in those environments. Okay, so when we look for the solar system, right, it's just an artistic conception. We see like these planets with different sizes and physical environments and chemical environments as well. So it seems very nice and very organized, but actually the solar system in the beginning was not like that, right? So basically, this cartoon tried to illustrate the solar system that we have now, like here, but also all the previous stages until the giant molecular cloud. So actually, this cartoon tells us that in this giant molecular cloud, there is some evolution, physical evolution and chemical evolution that goes to some collapsing core, then a protostar, then a disk, and finally we have the solar system. So, it's nice that you have a cartoon that's like that, but let's look into a real image, right? So this is a real image of a molecular cloud. This came about 2 years ago. This is part of the first observation, one of the first observations of the James Webb Space Telescope that targets this specific molecular cloud that's called Chameleon-1. So this molecular cloud was observed as part of the ICH collaboration. So ICH is a very big collaboration that we have in Leiden, and the PI, the lead of the program, is the Professor Melissa McClure, and I also had the chance to work on this data. And it's exceptional data. I'm going to show some more results later. But this is a real image of a molecular cloud. And you see like this, all these structures that you never saw before James Webb. And we see all these objects behind, so we can use the light from these objects behind the cloud to study the chemical composition of the cloud. That's what makes this very exciting. So, moving on, when we go now, I forgot to say that the physical conditions in this cloud is very cold. So we have temperatures of about 10 Kelvin. So this is like minus 263 Celsius. So it's very, very cold. And also, these molecular clouds are composed by gas, right? So here we have hydrogen, molecular hydrogen and atomic hydrogen. And also we have some particles that are called dust. Right? So these are basically composed by some silicates and carbon as well. So this makes the composition of the molecular clouds. Right, now going to the next stage, to the protostellar core. When this molecular cloud collapses, basically what we have is a structure like that. So we have some magnetic field here as well. And what happens is that during the collapse, we have this kind of a structure that looks like an hourglass, right? And this process also brings a lot of material to the core of this object. And when it brings this material, it also ejects in these bipolar outflows. That's the material that you see in these both sides. And here in the middle, we have what we call the protostar. It's not a star yet, but it's a baby star, so it's still like being developed. And basically, we also have this shadow. So this is also a protoplanetary disk. So with the evolution of the system, basically this material is going to dissipate after a few millions of years. And then we get to the next stage, that's the protoplanetary disk. So here is a real image of a protoplanetary disk, right? And basically we see like this dark lane, that's basically the light that's obscured in this region. And we have light that's reflected in, above and below the disk. So we have like this kind of structure. So just for you to have an idea, this size that I'm showing here is like 40 times the distance from the Sun to Jupiter. So that's very, very big. so we can put our solar system here like easily. So that's how all the planetary systems they evolve in other parts of the universe. Also, if you see another, if you change a little bit your tool and see a protoplanetary disk in another wavelength, you can see this kind of gaps. And these gaps could be, for example, the formation of the planets. They are curving, for example, this creating these gaps in this protoplanetary disk. So protoplanetary disk is also very active, right? A lot of physics and chemistry happening there. And after that, of course, we have the formation of the solar system, the planets, the mature planets, and something that we have nowadays. Right? So this is a kind of a very quick overview of stellar formation and planetary formation since the beginning of the molecular cloud. So very likely that our solar system looked at something like that in the very beginning. Right, so if you go to a dark place and you look to the skies, you may see something like this, right? I think that's an amazing experience. If you never did that, I recommend, because you see like the structure of the Milky Way, and you see all these stars spread around. But actually, we also have not only the planets in our solar system, but also we have the exoplanets. So exoplanets are planets that are in other parts of the galaxy. They don't belong to our solar system. And they come with different shapes and chemical environments as well. And our goal is just to understand a few things, right? So first we have to identify those, and nowadays we have more than 5,000 exoplanets discovered. So it's quite a lot, but we have many, many other candidates. And the final question that we want to answer is, how many of these planets or exoplanets life could have flourished? Right? So that's the main goal, that we want to identify exoplanets and search for life in those exoplanets. Okay, so now I'm talking about solar system, planets, and also the molecular cloud. But what we want now to understand is how the chemistry that happened in the beginning can evolve from the very first stage to the last stage of the planets. Right? So, and oopsie, yep. Too fast, sorry. Yes, so we have to think about the chemical elements, right? And because life depends on these chemical elements, we have a lot of oxygen, carbon, hydrogen, nitrogen, other minor species as well. And we have this very famous quote from Carl Sagan saying that we're made of side stuff. And it basically means that the ingredients that you have for life, they were, once they were available, present also in the universe. So, this also motivated many other studies, and including, for example, these scenarios about the origin of the life. Right? So if you think scientifically, there are basically two hypotheses about the origin of the life on Earth. That are basically some ingredients that were formed on the primitive Earth by some biogenic processes and abiotic processes as well. And then this creates some prebiotic soap, and then some polymers, and finally generated some ingredients for life. However, there is another current of understanding, say that some of these ingredients, they came to the Earth from space, right? Some extraterrestrial delivery of material. Here I'm not talking about the famous panspermia, that basically is just like some ingredients, like some complex molecules that has carbon, oxygen, nitrogen, that were available in space. They went to the comets and then were delivered to the planets later on. Okay, so my talk is going to be focused on this part, the organic delivery from space. Right. Okay, but before we go there, basically we have to think that the space is not some simple environment, right? It's a very hostile environment. And for example, if you look for Earth, basically we have like this pressure, temperature conditions, and low radiation field that allows life to develop on Earth. But now if you go to the interstellar medium, basically what we have is that the pressure really goes down. Here we have like 10 to 3 hectopascal, but here it's 10 to minus 18, right? So the pressure is very, very low in this type of environments. And the temperature as well, as I said, like in the molecular cloud, we go to minus to 60 Celsius, and this radiation field is very strong. So how is that possible that molecules develop in such very harsh environments? So, I have to test this hypothesis, right? And see if we have complex molecules in space. And here I introduce you to the world of astrochemistry. So astrochemistry is an interdisciplinary science that combines basically three things. One is the astronomical observations, experiments, laboratory experiments, and the computational modeling. So if you are interested in joining astrochemistry at some point of your life, you can join one of these branches and you'll be very welcome. Right, so starting from this department of the observational astrochemistry, let's look again in this molecular cloud. This was one of the first images of the James Webb Space Telescope. And in these conditions, where the temperature is very, very low, we can have a formation of a very specific type of material. So, I said that we have grains that looks like that, right? But this is a very cold environment, as I said. So, the atoms and molecules, they come to the surface of the grain, and they stick there, and they move around. And they create things, like, for example, the red is oxygen, the white is hydrogen. Here we have H2 going to gas phase. And here we're going to have another formation, like OH. Another, here is O2. So another hydrogen comes, and we have another formation of hydrogen peroxide. So basically, we have the destruction of the hydrogen peroxide. But the point is, when you see that in a long time scale, we have the formation of a mantle. And this mantle, basically, it creates a very cold surface or material around the grain. And this is what we call astrophysical ice, right? So we have ice on Earth, you know, like in a fridge or other types of environments. But in space, you can also have ices, and they are formed with this process. So the atoms go to the surface of the grain, they react, and they form molecules. So, and that's very important because actually, this is the stage where the complex organic molecules are formed. So that's very important that we understand the chemical composition of those ices, right? Okay, so for that, in order to understand that much better, we just need $10 billion, right? So that's all the cost of the James Webb Space Telescope. So if you don't know yet, actually the James Webb Space Telescope started to be planned in 1990. That was the first sketch of the James Webb Space Telescope. But this was only launched into space in 2021. So, long time. So this was the rocket bring Webb to space. Was the last goodbye to Webb before we saw him for the last time. So, Webb carried a very precious instrument that's called MIRI. And also MIRI was developed partially by NOVA. So if you don't know NOVA, NOVA is the astronomy Dutch school. So a lot of money from the Netherlands went into the construction of MIRI. And if you are not convinced that Webb is very cool, I'm going to show a comparison here. So this is a region in space with some stars. And this was observed in space by this telescope called WISE. And you see this image. Looks nice, but we can improve that. So another telescope went into space, Spitzer, observed the same region, and now we have some structure. That's very nice. Now we have Webb, and that's how it looks like. Right? So Webb is very, very powerful and very sensitive. And now we're taking advantage of this sensitivity to understand the chemistry in space. Okay, so as I said, we have this molecular cloud. Let's see which kind of chemistry we have there. So we have these two objects behind the cloud, and these objects, they emit light, right? Radiation. So the infrared light interacts with the material in this cloud, and now we have some absorptions that I'm going to show in the next slide. So, what's that? This is actually the two spectra. So in the y-axis, we have the intensity of the light, and here's the wavelength. So we see many absorption features, right? And these absorption features, they are associated with different molecules. Like for example, here we have, in 3 microns, we have water ice that I showed before. Here we have like carbon dioxide, carbon monoxide, and here we have the silicates, that's the dust grains that I talked before. So the molecular cloud does not only have water, but you have like a different chemical composition there as well. So how we know that, right? That's a fair question to ask. So for that, actually we have a laboratory for astrophysics in Leiden, and we have one setup that's called Nurseries. And this setup can simulate the chemical conditions of space. So we can have like experiments at 10 Kelvin in this type of pressure. So we do like a deposition of some gases on top of a substrate that's very cold, it's a metallic substrate sometimes, and then we can form like ice surface as well. So after that, we can calculate the spectrum, we can measure the spectrum, and then we have that, like water molecule vibrates because it also has energy in these vibrational modes. And then it creates like these profiles, like the 3 micron band, the 6 micron band, the 12 micron band. Right? This comes from this kind of dancing of the water molecule. But now if you have another molecule that's more complex than water, like acetaldehyde, we have like 2 carbons, some hydrogens, oxygen, and when this oxygen and this oxygen and this carbon, they stretch, they create this band here. So that's how we know that we have acetaldehyde, right? So that's how we do a combination between laboratory astrochemistry and the observations. So I talked about the ICH, the molecular cloud with different chemical compositions, but now let's look to another type of object, the protostar, I talked before, and see which type of molecules we have in these protostars. So for that, I worked with this another collaboration that's coordinated by Professor Vina van de Soek, and we observed that. So this is a spectrum of a protostar, looks very similar to the other one, right? So you say, yeah, perhaps we don't have much surprise there. However, let's give a closer look. So for that, here I'm just going to say I applied one tool that we have. So this code was developed by me and by other collaborators when I was in Copenhagen. So it's a software that's called Enigma. And what this software does is just search and find the best combination of the laboratory data that fits better the observations. So Enigma stands for the composition of infrared ice features using genetic modeling algorithms. Right? Okay. So this is one of the results that we have. So in black we have the observations from James Webb, and in green we have the final fit using the Enigma fitting tool. So what's that? I'm going to guide you a little bit here. So here we have the transition from this molecule, it's called methane. We have a lot of methane on Earth, right? Another molecule that perhaps is not so familiar to every one of you, but perhaps some of you already know. It's called OCN-. Then we have SO2. Then we have another special ion that's called chlorate ion. And here we have the first signature of a complex organic molecule in astrochemistry. So is ethanol. I know that a lot of you are drinking ethanol right now. Okay? So ethanol can also be found in space. And this actually was started, this type of research started many years ago in Leiden as well. But only now, in March of this year, with James Webb, we are able to identify ethanol in space for the first time. And this is the signature of ethanol in space, that we have these functional groups. So now we have another molecule, that's formic acid, methylformate, that's another special molecule, and acetaldehyde on this part here. We're going to see acetaldehyde showing up. And finally, here we have another molecule that's acetic acid. So all combined, we have what we see in the observations. So Enigma searched for that, found that we have 3 complex organic molecules, ethanol, methylformate, acetaldehyde, and acetic acid. So this is the first time that we detected securely complex organic molecules in the solid phase in space. So this came out very nicely. If you go to Google at some point and search for ethanol ice in space, you're going to find this press release from NASA that says, cheers, that we found some ethanol on the ice ingredient for worms, right? So basically these molecules, they are important because once they are delivered to the planets, they can trigger life at some point. That's what we think that could be happening. So this also was the part of the press release, And there was this other journal saying that they found margarita in space, but of course not there yet, right? We have water, we have alcohol, but then perhaps a few more ingredients for the margaritas. Okay, so I want to conclude my talk by saying that the ingredients for life, they are present in space, and this is important because it's even before the formation of the stars and planets. So can you imagine that even before the formation of Earth, the ingredients for life, they were already available in space. And the second thing is, this material will become part of the newly formed planets, right? So which kind of chemistry can you trigger after they are embedded in those planets? So thank you very much. Yes. People who has questions? Yes, sure.
The thing that worries me is the delivery system. If it's a sort of meteorite or asteroid, it's, as it plummets through the atmosphere, it's going to get extremely hot. And most organic molecules boil at an old 78 degrees Celsius. It's going to be destroyed before it reaches the surface. So how does it actually get delivered to the surface of the planet?
Yes, that's a very important question. So there is a thing that actually we don't know. I don't know personally if these molecules are going to survive the delivery process itself, right? But the point is, these molecules, they are not unnamed on the cells. Actually, when these molecules are present in the ice, so basically I talked about 10 Kelvin, 15 Kelvin, but when this material it is warmed up to room temperature, like 300 Kelvin, they also change chemically, and they produce another type of material. And this type of material, they are very, very hard to dissolve. So we have to think about these complex molecules not like an end, but as a step forward to the more complex chemistry. And we have evidence of that already in the laboratory. And for example, when we have this type of material, we combine, for example, irradiation, right? So there is a type of experiment that you can do, that you have the ice at 10 Kelvin, like water, ammonia and methanol, and things like that. You have some UV for a few hours, and after that, you can warm up the material to 300 Kelvin. Most of these volatiles, they are going to dissolve, but there is something that sticks there. So we can do some very specific chemical analysis, and we have found that this chemical analysis can produce, for example, riboses, right? And it can also produce some carboxylic acids. So this material, they are the most important that we want to find it. But they started not from water or methanol itself, but they have this between pathway that starts with acetaldehyde, with ethanol, with acetic acid.
Still doesn't answer the question though. 300 Kelvin is room temperature. I'm talking about 3,000 Kelvin when coming through the atmosphere.
Yes, so then I can go a little bit forward, right? And say if you, for example, look at meteorites, they already are here. They already survived the delivery process. If you do the chemical analysis of these meteorites, we can find all the nucleobases that we have for DNA. So somehow it's possible that this material can survive. Not perhaps the volatiles, but if we have like complex chemistry happening in space that ends in these nucleobases, from the meteorite evidence, we can know that they can survive. But of course, it's that's science, right? I think there is a lot of people working on this type of research. That's not me. There's more like smart people doing that. And I know, like, for example, from other groups, that they simulate, for example, this delivery process. And what happens is, if this organic material is very embedded in the solid, in the dust environment, what happens is that the heat transfer in the meteorites is not so efficient. So if you have some material underneath the first surfaces of these meteorites, they could survive. That's a research that I heard recently from a group in Vienna. So it's possible somehow.
So it comes to an abrupt stop on the Earth's surface, then back.
Yeah. So again, I couldn't.
Until it comes to an abrupt stop on the Earth's surface and then, gets ejected into the atmosphere.
Yeah, I don't know if it's
the kinetic energy of it hitting the Earth's surface will produce an enormous crater and blast ejector all over the place, and it'll, destroy all this energy.
Right. Yeah. No, I agree. I think we have to be, in fact, critical with those results. Yeah. Thank you. Yeah. Go ahead.
It was a short, model, and a dust particle and molecules started forming.
Yeah.
And you said it's like a good environment for actually forming these molecules. But what exactly the dust particle consists of itself?
Yeah, so we have basically two components, two types of silicates. One is called olivine, another one is pyroxene. These are the main components of the dust, right? But we have evidence that these only two are not the only ones, but they have a little bit more like a silica, other crystalline silicates that they call fossilite, and a few other materials as well. But the main composition is olivine and pyroxene. Yeah.
A bit related to the question just now. So I was a bit confused about the experimental setup, because that was done on a metallic surface, so which is very different from silicates. So is it now the idea that the silicates are the catalytic surface for smaller molecules, and then the ice surface is the catalytic surface for the more complex organic molecules?
No, not that way. Yes. So basically, what happens is that if you have, so we can also do experiments with silicates as well, but it's not as simple as we have like this type of substrate, right? So that's the thing. If you have this type of experiment, the goal of this is basically to get the infrared spectroscopy information of the ice that you have there. So this material is transparent to the infrared light. So we put some material here, and then we have infrared light to get the spectra afterwards. So this is ideal for this type of work. However, if you want to do chemistry or chemical reactions, right, we can also do here, but you have to keep in mind that this is not the right surface that you can do, right? So for that, there are other people, not in Leiden, but for example, there are groups in Spain that you can also simulate the silicates itself, and you can try to do reactions there, right? So basically, the chemical, like the binding energy is going to change, all these kind of things, and of course, it's going to affect your final product. That's true.
So this is mainly to get the final spectrum sort of correct. The same that as the Nick does in the algorithm. Yes. This does this. You're just trying to match the spectrum as well as possible.
Yes.
But
exactly.
don't measure reaction speeds and that sort of stuff.
No.
Yeah.
We can do here, that goes a little bit in that direction, is if you have, for example, water and ammonia, right? So basically water has some absorption features, ammonia has other absorption features, but when we put those together, you have some bonds between the hydrogen from water and the hydrogen from ammonia, and they create some bumps that didn't exist before. We can also do here, do this type of mixture, so we can simulate as well the intermolecular interactions.
I think one more last question.
Yes, zero.
So this research is based on this initial image it shows from James Webb, and we extrapolate to other regions in the universe?
No, we're not extrapolating because we also have data from other sources.
Okay.
Yes, so we are doing analysis for these other sources as well. But I couldn't show today. Yeah, but they exist. It's very nice. Yeah, thank you very much.
We end there.